In this video, we're going to talk about the reactivity of carboxylic acid derivatives. So in terms of reactivity, the acid halides are the most reactive, the acid anhydrides come in next, and then the esters and the amides are the least reactive. Now, when we have any carboxylic acid derivative, the reactivity is going to primarily be determined by induction and resonance, and to a lesser effect, sterics, and then the quality of the leaving group. Now, I'm not going to give you, other than knowing this general trend, I'm not going to give you a series of carboxylic acid derivatives and make you say which ones are more or less reactive, but I do want to see if we can explain using induction and resonance why, in general, acid halides are the most reactive and why the amides are the least reactive. So we said that the acid chlorides are the most reactive of the carboxylic acid derivatives. And let's consider induction and resonance to explain why that is. We know from last chapter on aldehydes and ketones that the carbon of the carbonyl group is relatively reactive due to its electrophilicity. The presence of the chlorine atom as a result of induction enhances that electrophilic character because it removes electron density due to its electronegative nature. When we consider the three resonance structures that we can draw for the acid chloride, of course, we can move the pi bond up to the oxygen, giving us a negative charge on the oxygen and a positive charge on the carbon. And we saw this from the aldehydes and the ketones that, in addition to the induction of the oxygen, this resonance structure is a big part of why this carbon is so electrophilic. We can also imagine drawing this resonance contributor where one of the pi bonds from the chlorine comes down to give us a positive charge on the chlorine atom. This is not a significant resonance contributor because the p orbital on the carbon is much smaller than the p orbital on the chlorine atom. Because those orbitals don't overlap effectively, this is not a significant resonance contributor. And so the chlorine doesn't actually add any electron density to this carbon atom as we might expect. So this resonance structure is not significant, and so chlorine doesn't really have any resonance effects. It just removes electron density from an already electron-poor carbon atom, making it very reactive and very electrophilic specifically. In comparison, if we consider the amides being the least reactive, to explain that, again, let's look at the two most important factors, induction and resonance. So first of all, nitrogen is certainly less electronegative than oxygen, somewhat less electronegative than chlorine, so it's less effective at removing electron density from the carbon than the chlorine atom was. And then if we consider the resonance structures, so we've got these same two resonance structures that we had for the acid chloride, but when we consider this third one, again analogous to the third structure we had for the acid chloride, this is a significant resonance contributor. So the size of the p orbitals on the carbon and the nitrogen atoms are relatively similar. That allows for effective overlap, so we can make this pi bond. And so as a result of resonance, the nitrogen donates some electron density back to the carbon atom as a result of this double bond character from this third resonance contributor. So the reason the amides are less reactive than the acid halides is because nitrogen is less electronegative than chlorine, so the induction effects are less destabilizing, and as a result of resonance, the nitrogen can donate some electron density back to the carbon, again reducing its electrophilicity compared to the analogous acid chloride. Now we're going to spend the rest of this video, and frankly most of the rest of this chapter, considering nucleophilic acyl substitution. So carboxylic acid derivatives can undergo a reaction where we replace whatever this Z group is, right, an OH for carboxylic acid, or chlorine, or an alkoxy group if it's an ester, whatever it is, with some other nucleophile. Now aldehydes and ketones could not undergo this type of substitution reaction. All of the groups that we have in our carboxylic acid derivatives can form as either a good or at least a reasonable leaving group. In the case of aldehydes and ketones, where rather than having some heteroatom here, we have either a carbon or a hydrogen, C minus and H minus are terrible leaving groups. They're incredibly unstable. And so we don't see these reactions in aldehydes and ketones, but we do see them in the case of carboxylic acid derivatives, where this Z group is a much better leaving group than either a carbon or a hydrogen. Next, we want to consider the mechanism for this nucleophilic acyl substitution. In my opinion, this is one of the hardest things we've done this semester, and so I can't stress enough how important it is to practice drawing the mechanisms for these reactions, because they're all going to share the same two core steps. Whether we have additional proton transfer steps and where those proton transfer steps occur is a fairly subtle difference, and so it takes a lot of practice to get good at drawing these mechanisms. And we're going to spend a lot of time on these, and so we're definitely going to ask you to draw a lot of these mechanisms. And so again, I can't stress how important it is to practice this material. So the two basic core steps that we're always going to see is we have a nucleophilic attack followed by the loss of a leaving group. So that's pretty straightforward. The intermediate has a different hybridization and shape than either the starting material or the final material. Both our starting material and the final material are trigonal planar and sp2 hybridized, whereas our intermediate is sp3 hybridized and tetrahedral. And so this intermediate is often referred to as the tetrahedral intermediate. Okay, so let's look at our first example. So here we have an acid chloride reacting with a methoxy group. Right, and our reagent here was probably something like sodium methoxide, where the sodium just acts as a counterion. So we start with nucleophilic attack. The lone pair on one of the oxygens from the methoxy group attacks the carbonyl carbon. Pi bond on the oxygen becomes a lone pair, giving that oxygen a negative charge. Then chlorine is an excellent leaving group, so the chlorine falls off as a leaving group, and we reform the carbonyl group by getting that double bond back between the carbon and the oxygen. So this is the most basic example of nucleophilic acyl substitution, where we don't need any proton transfers at all in this reaction. We just have the two core steps: nucleophilic attack, loss of a leaving group. Now, we've studied other substitution reactions largely last semester when we spent a lot of time on SN2 and SN1 reactions. The mechanism for the nucleophilic acyl substitution is different than either SN1 or SN2. We have the same basic core steps, nucleophilic attack and loss of a leaving group, but the ordering is different. In an SN1 mechanism, we first had the loss of a leaving group, then the nucleophilic attack, right? In this case, it's nucleophilic attack, then loss of a leaving group. The other thing to note is it's not the same as an SN2 process. In an SN2 process, the nucleophilic attack and the loss of leaving group all happen in one mechanistic step. It's a concerted process, right? That's not what's happening here. Here we have first nucleophilic attack, and then in a separate step, loss of a leaving group. So it's important not to draw these as a concerted mechanism. Now, as I mentioned, what can make these mechanisms different is when we have different reagents in different substrates, it may be necessary to have proton transfer steps. And one of the main things that we're going to be worried about for these proton transfer steps is that we don't form inappropriate acids or bases depending on the conditions that we have. So I think what's important to remember is that under acidic conditions, don't make strong bases, right? We talked about this last chapter when we talked about drawing mechanisms. We can't have acids and strong bases present at the same time. And so if we have acidic conditions, we can't make strong bases. Therefore, we're probably not going to make new negative charges during the mechanism. If we do, then we have a problem, and we need to use proton transfers to avoid forming those negative charges. Conversely, if I'm in basic conditions, don't make strong acids over the course of the mechanism. So we're rarely going to form new positive charges when we have basic conditions. All right, so I want to talk about drawing correct mechanisms for the rest of this video, and we'll have an example in the next video. So again, what we're worried about here is all the participants in a reaction mechanism, so the reactants, the intermediates, the leaving group, should all be consistent with the conditions employed, right? So don't make acids when we're in basic conditions, don't make bases when we're in acidic conditions. As an example, let's consider the acid-catalyzed hydrolysis of this ester to convert it into a carboxylic acid. So this is an example of nucleophilic acyl substitution. I'm replacing the alkoxy group with a hydroxy group, right? So I've just swapped out the Z groups. Now we're going to do this under acidic conditions. So in the last example of this, when we had a methoxy group and we attacked an acid chloride, it was fine to do the nucleophilic attack first, because if we've got a methoxy group, we're in basic conditions. Here, we're specifically told that we're in acidic conditions. And so let's look at what happens if we try to do the nucleophilic attack first, right? So the water attacks, pi bond becomes a lone pair on the oxygen, right? We've made a new negative charge. A negative charge on oxygen, as we know, is very basic. And so if we attack with the OH first, we've made a strong base, and we can't do that. That's bad. So let's see what happens instead first. How can we use a proton transfer to get around the formation of this strong base? So pretty much any time we're under acidic conditions, a proton transfer will generally be the first step, because when I do this proton transfer, that makes this oxygen positive. And so now when I come in with a water, right, I didn't make any new negative charges, so I'm not creating a strong base. So by protonating my substrate first and then doing the nucleophilic attack, I can avoid formation of that strong base. And because I'm in acidic conditions, I had to do that. And so, actually, I guess I just drew this on the last slide, but it doesn't hurt to see it again, right? By protonating our carboxylic acid, or I'm sorry, by protonating our ester first, then when we have the nucleophilic attack of the water, we don't form that negative charge. We're not forming a strong base, and so that is an allowed step for a mechanism in acidic conditions. Okay, in the last example, we were under acidic conditions, and so we can hydrolyze esters to form carboxylic acids with acid catalysts. We can also do it with basic catalysts. Under basic conditions, we don't start with a proton transfer. In fact, we can't start with a proton transfer because that would make a new positive charge on an oxygen atom, right, forming a strong acid, which we can't do under basic conditions. Right, under basic conditions, OH is going to be our nucleophile, and so when it attacks, having an O minus, which is a strong base under basic conditions, is okay. And in fact, we're not even making a new negative charge. The negative charge existed on the OH to begin with. And so this first nucleophilic attack is allowed under basic conditions. Now, if we were to convert our ester into an amide, where we're using an amine as the nucleophile, it will also attack the carbonyl group first, without the carbonyl group first being protonated. If you remember, amines react best under basic conditions because these amines themselves are slightly basic. If we were in acidic conditions, and these guys would protonate and they wouldn't act as effective nucleophiles. And so again, because we're in basic conditions, it's okay to form the negative charge on the oxygen. Just be careful. Another thing to keep in mind when you're drawing mechanisms to make sure that they're appropriate, right? Don't make new negative charges in acidic conditions. Don't make new positive charges in basic conditions. It's okay to have positive and negative charges together, but don't have two charges of the same type when drawing these mechanisms, right? So don't have don't make two negative charges or two positive charges at the same time. That's not going to be stable. And it's okay to have the positive charge on the nitrogen, because nitrogen being less electronegative than oxygen, it's okay to have that positive charge on the nitrogen atom. All right, so for these proton transfer steps, what makes it challenging is for these nucleophilic acyl substitution reactions, we always have the core nucleophilic attack and the loss of a leaving group, but depending on the conditions, we could have proton transfers before the nucleophilic attack, we could have proton transfers in between the nucleophilic attack and the loss of a leaving group, and we could have proton transfers after the loss of a leaving group. And so depending on the conditions, we have to decide whether we need these proton transfer steps or not. Okay, let's finish off with another complete example, and then I've got another video that's just another example of drawing the mechanisms for these nucleophilic acyl substitution reactions. So here I have an acid chloride where I'm going to react it with water to form the carboxylic acid. Now, we're reacting this with water, so we're not under acidic or basic conditions. So when we're not in acidic conditions, it's okay to start with a nucleophilic attack. It's okay to make this negative charge on the oxygen because I'm not in acidic conditions. So we start with a nucleophilic attack. We form the tetrahedral intermediate. Then the chlorine pops off with the loss of a leaving group, and we reform the carbonyl group, but our compound is still charged, and we want to form the neutral carboxylic acid, so then the last step has to be a proton transfer to give us the carboxylic acid. I think determining whether there's a proton transfer step at the end is generally pretty easy. If we have the final product is charged, either negative or positive, we're going to need a proton transfer to give us the neutral final compound. All right, and so then this mechanism was pretty typical for the pattern of acid halides. With acid halides, I don't need proton transfers at the beginning or the middle, but I do need a proton transfer at the end.